My name is Irena, and I work here at FINI as a geologist. I'll talk today, I'll introduce you to reflection seismic. It's a way to look into the Earth. To begin with, I'll tell you something about my background within this area. I worked a lot with it during my studies, and also my thesis was about reflection seismic, so I interpreted a lot. But in this lecture, we will go through the basics because it's a very large topic, and there are many details we can go into, but we won't do that today. First of all, I'll tell you something about the purpose that this may be used to. It can be used to find oil and gas, and it's also used for engineering, surveying, and environmental surveys. This picture, this kind of photo we see here. Also, it is used for if you want to find some minerals or coal in the underground. We also use reflection seismic. And at last, it is used for crustal studies to study how the top part of the Earth developed. So, first, a short introduction to what is reflection seismic. We see here we have a source here, and we have a receiver. What happens is that we have an explosion, some kind of explosion, or a signal is sent out, and then the wave, we call it a P wave, it will travel down until it meets something that has a different, it's a different layer. So it can be because of that the density is different. I'll explain it in a moment what the density, how it affects the signal. It will travel down to when it meets something that's different, and then a part of the wave will be reflected back up to the receiver, and it will receive the signal, and it will always be reflected back in the same angle. So if we say there are 45 degrees here, it will be 45 degrees here as well, or 20. It is always reflected back in the same angle. But not all is reflected back. A part of it has to continue, so we can get like a birthday cake of a lot of layers down. So we can see not only one layer, but we can see the next layer as well, and the next layer. So that is very briefly what reflection seismic is. And this wave that travels from here, that we create here, it's called the P wave, like P, and the P stands for primary. It's because when we have this explosion, it's the first wave to arrive to the receiver. So that's the P wave. It's a primary wave. It is also similar to the sound wave, so we can also call it a sound wave, or we can call it a pressure wave because it creates pressure. So it will. There's a pressure difference created in the path of the wave. Yes, I think that is very in simple terms what this is, reflection seismic. So it is reflected from a boundary here and from the source to the receiver. Okay, I'll explain a bit more about the wave, what a P wave is. So if we have an explosion here over to the left, then it will create a pressure in the air or in the material that's underneath, and then we will have some. You can see there's expansion and there's compression. So it travels through the material, and the material is pushed together and extended a bit. That's how the P wave travels through a material. As you can see in the lower picture of the photo here, it is the same that happens when we hear a sound. When I talk now, I create a pressure in front of my mouth, so you can hear it in the other end, because and these particles that are closer together and further apart, that makes the sound. So it is the same principle. So we see expansion and a compression, and then when the wave has stopped, then they will go back to the normal as they were before. Yeah, there are several ways to collect a reflection seismic. You can do it on land and you can do it on the ocean. When we do it, collect reflection seismic on the ocean, it's called offshore, and you use the both. Then you see here in the top part we have a photo from reality, and then there's a sketch, and we see how the boat sails, and it has long cables, maybe it's several kilometers back of the boat, and then in this just next or just behind the boat, small explosions are made, and then they create this P wave as I talked about, and it will go down to a layer where it meets a different layer, and then it will be reflected back, as you see here, and it will be received by several receivers, as I showed you in the former photo, and a part of the wave will continue, and then when this part of the wave meets something different, it will again reflect a part back, and then a part of the wave will continue. Of course, this can't go on forever. At one point, the P wave will be so weak that we won't get any signal back, and the signal gets weaker and weaker further down we go into the layering. This is on the ocean when we collect seismic. Then we can also collect seismic, reflection seismic on land. That's called onshore, and for that we use big, large trucks, and they have, like in the middle, they have a stumble. So and they like put it underground, as you can see on this photo, and then it starts to vibrate to create this P wave, a pressure wave. And it's the same happens. We get the signal, it goes down, and it's reflected at a boundary where the material is different, and we will receive the signal in the receiver again. Yeah, all seismic surveys, we call a seismic survey. That's when you go out and you collect a lot of these seismic samples. So you do a lot of measurement in a large area, and then you can put them together to a picture at last after the survey. But before, I will show you some examples and show you how it looks. I first want to talk about what is important for the signal we get back, and why it is different. So next slide here, I'll talk about rock properties shortly, and density of minerals. If you know, I don't know if you know, but all rocks have a density. Within the basaltic rock, that's a very common rock on the Faroe Islands. It's all around. So but this basalt, it's composed by 3 different minerals. But you can't see it with your eyes because it's very small minerals, so you can't see it. Maybe if you have a loop, you can see something, but they are very small. And they are olivine, and you can see here the density is 3.3 gram per cubic centimeter for one part olivine that is 1 times 1 times 1 centimeter large. Then we also have pyroxene and plagioclase, and you can see that the densities of these three minerals are different: 2.7, 3.4, and 3.3 gram per cubic centimeter. This means that the density of the basalt, it's not fixed, because we don't know how much olivine or how much pyroxene or plagioclase there are in the basalt. It can be more olivine sometimes and less sometimes. It depends on the conditions when this rock is made. So it is important to say that we know maybe that the basalt has it can have a range of densities, but it doesn't have a fixed density. But on the other hand, if we look at specific minerals that makes the rock like olivine, they are quite specific. They can vary a little bit, but not as much as when we look at normal rocks that are composed of more than one mineral. Yeah. And I forgot to say that if you have any questions or something, you are, of course, welcome. You can write in the chat, then just ask, and I'll try to answer it later on. Yeah, so that's about the density of minerals within a rock. So, as you might guess, now we have many kinds of rock. We can have basalt, as I showed you before. We can have a sandstone, and we can have a pumice. And I don't know if you know something about these rocks, but pumice, this is a very light rock, and it's because there's a lot of air, a lot of bubbles in this rock. So, and of course there are also minerals, but the air in the rock is also a part of the density of the rock. So this is why pumice is very light, and often it can be lighter than water, so it can actually float on water. If you have some water and you put a small pumice stone on top, it can float. But normally, you know that when you put a stone in water, it will sink to the bottom. So this pumice, it has a very light or low density, while sandstone and basalt, they are much more heavy. And but all these three rocks, they have a range of density. So sometimes pumice can also sink into water, but it can also be lighter. And the same with sandstone. It has a very wide variety of density. And the thing is, the density is very important for our reflection seismic, because that is what affects the velocity in the reflection seismic. And now I'll show you a graph here. So we have different kind of rocks. What kind, it doesn't matter. Here are just some kinds of rock. You can see salt here and sandstone, as I told you before. And we can see that we have the P wave velocity, which means that's the velocity or how fast the P wave that is created when you have this explosion at the beginning of the survey. It's here in the x-axis, and we have the density of the rock here on the y-axis. And as you see, that a sandstone can have density in a sandstone can vary from 1.8 something to 2.5, around that. So that's quite a variety, but also, which means that the P wave, the velocity of the sandstone is also varying a lot. So it can have 1 kilometer per second and down up to 6 kilometers per second. So there is correlation between the density of the rock and the P wave velocity. So the chances, if you have a very dense, like very, very heavy rock, then the chances that you have a very high speed velocity, or the speed in the rock is higher. That's the case. That the denser the rock, then the velocity is often higher. But of course there are exceptions, but that's the rule. Yeah. So now you know something about that. That when we travel, we send this explosion, and the P wave travels through the rock, and also I forgot to say that rocks often get denser and denser further down we go, because they are more compacted. They, like in the top, they don't have so much on top, so they're not as compact as further down. That's one thing. And further down, we all often have more heavy minerals. As I told you before, we talked about minerals. They have different densities. So further down we go, the minerals are often more heavy. We can maybe have some iron, or like we have more heavy minerals. And that is why we often see that when we make this seismic survey and we go down into the earth, we often see an increase in the velocity of the rocks. Yeah. Okay. So now I will continue to the next slide. So in theory, I will talk a bit, like we have the basalt, the column here. This is from the Faroe Islands, and then we have in Denmark, there's a lot of chalk. And the velocity is different in these two areas. It can vary, but now I've taken the mean velocity of basalt and chalk. So in basalt, it's typically 5.25 kilometers per second, and the velocity of chalk is typically 2.25 kilometers per second. So now I have a question, and I would like you to come with an answer. So where do you think the ray travels fastest? Is it in the basalt, or is it in the chalk? Then I will tell you. I won't keep it a secret. As you can see, the velocity in basalt is higher than in chalk. It's 5.2 kilometers. So in 1 second, a P wave travels 5,250 kilometers, and in 1 second, a P wave in chalk travels 2,250 kilometers. So the velocity in basalt is almost twice as fast as in chalk. Yeah. And this can, then we talked about, before we talked about that the velocity, there was a correlation between velocity and density. So from this, we could say, okay, then basalt should be heavier than chalk, and which is that is the case. So it makes sense. So now one more question that I just answered. So the chalk has a lower velocity and the basalt has a higher velocity, density. Sorry. Yeah. Now I want to show you some examples of reflection seismic. I've tried to give you an explanation of what it is, and like the very basic thing, that what we can use it for, and how it works. So now I'll show you some examples here. First of all, I found this birthday cake. This is what we see if the cake is the earth, and then we cut into the earth, and then we can see like the structure in the cake. This is the same with the reflection seismic. We have the reflection seismic here section, and then we cut into the earth and we see it like a layer cake. We see from the top of the earth, and then we see, oh, what happens down through the earth. And we see a lot of changes because we see a lot of reflections. So that are changes in the earth. This seismic section is from east of the Faroe Islands, and here we have the top of the basalt, and that's a very strong reflector, and that's because the difference between there's some sand maybe on top and the basalt, it's a very large difference between the densities and the velocities in those layers. So that's why you get a very, very strong reflection here. And that's the same case. We have water here and we have the seafloor here. That's also a very strong reflection because there's such a big difference between the two, between water and then solid rock. Yeah, we can see here that's the unit that we measure in when we measure reflection seismic. So it's in milliseconds. So the rate travels down here and up again. It's measured in milliseconds. So maybe around 4,000 milliseconds down here. And this unit is also called two-way time. And two-way time is that this is one way down and then the other way. So we have the time like times two because we both go down and up. But it's called two-way time, and that's the normal term that we use when we interpret this kind of seismic sections. So this is, and we can see that there's a structure here and a structure here, and you can interpret this like when you look at it, you can say, okay, what happened? And you have a lot of ways to interpret this kind of seismic, but then you need a lot of time. I use 1 year for my thesis. Of course, it was a large area, but you can really go to detail. You can also make a smaller study to look at a smaller area and use less time, but it needs a lot of time. And of course, you need, when you interpret, if I interpret this, there's not one right way to interpret, because we have rules that we follow when we interpret, but sometimes another interpretation can be just as good as the one that I made. And it is hard to justify which one is the most right. Maybe you can do it if you then choose to go further in the area and make another study, maybe drill a well or make some other kinds of measurement. Then you can say, oh, this interpretation is more right than the other one. But you follow the rules that you have, and if you follow the rules, then one interpretation can be as right as another one. Yeah, so this is one seismic example. Then we have another one. This is south of the Faroe Islands, and you can see there is not as much happening. The lines you see here, that are some interpretations that are made a long time ago. But then you can choose a reflector and you can follow it. And in the end, when you follow a lot of reflections on a lot of profiles that are crossing, so you can have profiles like maybe on this way, this is the Earth, and we have profiles in this direction and that direction, and you can actually make a map where you can see maybe how deep there's down to a specific layer in the Earth. So this is another example. Here we see there's this irregular layer here. And this is an example from Danish area, actually. And in Denmark, in parts of Denmark, there is salt. And when salt is buried very, very deep, it gets under so much pressure that it can become kind of floating. So it's very ductile, it can move, and then it will, because it's lighter than the rocks on top, it will try to get up. So that's why this layer here, it tries to move up. And we see that the layers on top, they're affected by this movement. So this is just to show you some examples of that you can have very different seismic through around the world, and there are many things that you can see and learn from it. What happened a long time ago in our subsea or in our underground, and I think it's very interesting that we can, from this example, we can learn that okay, at one point there was salt here and not talk as we see today, as in an example from Denmark, and that it actually, even though that it's today not active, that it back then it is like it is changing through time. It's not, yeah. I think that's very interesting. It's, yeah, for me at least. Yeah. Okay. Now I want to show you one example. Just when I interpreted something, I choose some, we call it horizons, and then we say, okay, we follow one. It's called a reflection. So we follow one color, a line in the seismic section, and then we draw it on all the profiles. So here, this I choose to follow this one. Then I color the part underneath, so we see what belongs together. And from this interpretation, we can find, like, make a story. What happened? Why does this end here, and why didn't it end here? There must be a reason, and then we can make some research. Maybe there's something, an event at the moment that made this happen. And yeah, so that is one thing, that when we interpret seismic section, we also come up with a theory behind, like, okay, maybe this happened because we can see this on the seismic section. That's one thing. And then from the lines, like the interpretation made, the lines we draw on the photos from the underground, the reflection seismic, we can, maybe I did draw a lot of lines, and then from the top we can make a map. So this map is actually just, I've interpreted the seafloor on a lot of seismic section, and then I merge it, I made it, put it together, and then we can see how deep it is down to the seafloor. But as in the seismic section, this is also in milliseconds, and yeah, so it is in time and not in meter as we normally would measure down. But yeah, and that's one thing, one result you can get. Another result is this. This is what we would call a conceptual model. So you can interpret something, and you can have an idea in your head what happened, and then afterwards you can make a sketch or drawing of what you think happened, and then we make something like this. And there are many ways to do it. So this is just some examples how you can be, I don't know if you can say, but like you can get your message out of what you think happened in a specific area from the interpretation you made. So, and one thing that is also important, that reflection seismic is a easy way to cover a large area, like quite cheap. Of course, it's not cheap, but you can cover a large area compared to maybe drilling a hole or taking a core up. So this is a way to figure out where you want to make further studies, where you think, oh, this is interesting. Here I want to dig a hole, or what, like here I want to look closer on what happened. So actually, I hope you learned something. And if you have questions, I didn't get any yet, but if you have, you're welcome to ask. If not, we have a Kahoot now, where I hope you can get your answers from this lecture and that you learned something.
Question number 1. What of the following answers is not an alternative expression of P waves? Red, a pressure wave; blue, a Pokemon wave; yellow, a sound wave; and green, a primary wave. Five more seconds to go. So the correct answer is blue. A Pokemon wave is not an alternative expression of P wave. Great, all the answers were correct. Next question. And first, the results. Posilico was the fastest. Question number 2. Does the geological column of rock usually what happens downwards? Red answer, increase in density; blue, decrease in density; yellow, have the same density all the way; green, have a random density through the column. So the correct answer is it does increase in density. It was a red answer. 3 good answers. Very well. So we have a bit of change in our podium, but still many questions to go. So question number 3. Is there often a correlation between velocity and density? Red, seldom. Blue, no, there isn't. Yellow, yes, there is. Green, it is unknown. Okay, so yes, there is often a correlation between velocity and density. 3 good answers. Okay, some changes in our scoreboard. Next question. Question number 4. What happens in reflection seismic? Red, part of the wave is refracted. Blue, the entire wave is refracted. Yellow, the entire wave is reflected. Green, part of the wave is reflected. Five more seconds to go. Time's up, and the right answer is part of the wave is reflected. 3 good answers. Very nice. Let's have a quick look at our scoreboard. Okay. Question number 5. At what angle is the wave reflected? Red at 50 degrees, blue at 30 degrees, yellow at the same angle as the incident wave, or green at 45 degrees. Were you listening carefully? Okay, you have all the answers, and yes, the wave is reflected at the same angle as the incident wave. Very nice. So the 3 first places are very, very close to each other. Question 6 of 7. In what unit is the reflection seismic measured? Red in meters, blue in seconds, yellow in milliseconds, and green in kilometers. What is the unit? Remember, there's one correct answer. Yes, in milliseconds. Well, it wasn't, it didn't go that well, yes, but still we have one good answer. Okay, the very last question, number 7. What is the unit of reflection seismic also named? Red, OWT, one-way time. Blue, TWT, two-way time, yellow UAD, up and down, and green BAF, back and forth. Remember, it is best to answer as fast as you can. 5 seconds to go. And the answer is two-way time. Very, very good. So let's have a look at the final podium. So yes, Vasily go on with almost 3,500 points, and we have Christina and Maria too. Very, very well done. As usual, we're encouraging teachers to give you some tiny awards, maybe a good note. So thank you very much for your participation.